What I want to do is, for those of you who want to do it, get you to where you can download the machine learning example of this morning and run it under PureData. And if you don't want to do that, like if you hate PureData or something else, you can just follow along, or you can go have a sandwich or something. And I don't think this is going to take very long. The difficult part is going to be getting to where you can run PureData, and the easy part is going to be grabbing the package. And what I'm going to do to get it started is show you where the package is, so that those of you who've got PureData running can get there first. Hello, what was that? Okay, so I don't know why I have to do this, but I think normal people, if they type in msp.ucsd.edu, get the HTTPS thing. It doesn't matter, except this one you can actually believe that it's correct. And then what was it called? Fan PAW 23.zip. Oh, quite possibly, but I don't know how. Let's see. Actually, let me just copy this and throw it in a text editor or something like that. Yeah. I don't know how to do normal things like this. I just do bizarre stuff. How do you change the font size on this puppy? Oh, God. Is there a... Oh, I know. Let's do this. Copy, paste. Now I think I have probably a GUI thing that will work here. Yeah. Don't do anything the way I do it. Hit it, and it didn't do it. Oh, okay, right. There you go. Yeah, maybe. There. So here is, except with either this or with an S, as you prefer. And this will be a zip file that contains, let's see, well, it'll contain a few examples, including the ones that I was looking at this morning. And it also contains a compiled external object for PD that will work on, probably Mac Intel and probably not Mac M1. I can't remember now if I have it for let's find out. Okay. Patch machine learning. Hello. Okay, I'm just realizing as I'm saying this, I only have the x86 version of this for Macintosh, so those of you who are wanting to run on a Macintosh will want to run PD as an x86-64 program, which I have just learned to do. and if any of you is trying to do this, I will try to guess how you would do it from this machine and probably fail, but I know it's possible. The trouble with PD is that it is it's two programs, and when you just click on the thing like people do on Macintosh, you get the GUI, which is not PD, and then when PD starts up, it will start up with the native architecture, even if you told the GUI to run under Rosetta. So what you have to do then is to get the native thing to run under Rosetta, for which there is magic, but I have to tell you the magic. So is anyone here running, obviously, people here are running M1 Macintoshes? Okay, so here, all right, so let me show you what you might have to do. You will have to say, applications, well, whatever this is, PD, whatever, and then contents, and then resources, then bin, then PD. That is the actual PD program. And to run that from the command line in 86 architecture, you say arch minus x86x64, I think. Okay, and I'm going to just double check that. Yeah, I probably didn't get this exactly right. There is a, so what's it going to be? It might be IA64? Probably not. I think there's an underscore in there. How can you find out? No, come on. I did this just 2 days ago because Philippe Mannery is trying to run something in PD on, it's the philosophy art. Oh, come on. No. Did anyone find it? Ah. Oh, arch minus arch x86-64. Maybe, okay, this is it. There is misinformation on the web about this. Maybe it is arch minus arch. That's weird, but x86-64. Try that one and see if that gets PD up and running. Because the extern, the yeah, right. In other words, I have yet to realize that I have to compile. This happens to me every week or so, that some useful thing that I've done doesn't compile under some architecture change in some operating system or other, and this is an example of that I'm only discovering right now. Sorry about this. Okay. So that is now how you. This is how you launch PD in order to be able to run x86 externs within PD. You do not need to do this if you just want to run PD, but if you want to do this until I can manage to figure out how to compile fan for blah, blah, then you have to do this. Now, so what I want to do, okay, so first off, stop me when you have trouble doing any of this stuff, which will happen. The first thing that I think you will want to do is go get the, oh, it changed all my nice fonts. Oh, that's all right. Work, patch, machine learning, fan. So this should be the contents of the file that you are downloading. And where I propose that you start looking is, curve fitting.
Sorry, can you show again the SCP command?
Yes. It's right here, but let me see if I can get on one line. Ah! See if I'll get on one line. There it is.
No, the SCP command to download the SCP command to download.
Oh, that's just a URL. And that is, ooh, where did I put that? Right here.
So small.
Like that.
Okay.
What you're seeing is 1979 era programming style transposed with great difficulty onto the realities of 2023 computing. I simply refuse to join the modern age, and that this has its certain disadvantages. That said, the World Wide Web only came in about 1994, at least where I could see it. So we're really only going back about 29 years in time.
So I don't have the name of the host.
Of the host, msp.ucsd.edu.
Okay, this is the host.
Yeah.
Okay, then you should have
Well, yeah, I think what you do is you just take this and copy it right into your browser, and then you get this,
Okay.
right? Sorry, I should have made a simpler URL.
So it says that it's not accessible.
What?
Is it working for you?
Not accessible. Oh, no. Oh, sorry. Okay. Okay, that's bad. That's something that I don't understand about HTTPS that I have to learn. Because I'm trying to make everything only HTTPS, but I still get these weird server hoo-has. Okay. Now, okay, so what I'm going to do is try to get those of you who have PD working to be able to run this patch, and then go back and try to get people who don't have PD working to get PD working so that they can run the patch. Are there people who don't have PD itself working here? Probably, yeah? Oh, yeah. Okay. All right, so we will want to spend some time doing that. So let me show you what's up here, and then you can decide whether you want to go any further. Okay, so this is a very simple machine learning example, which I talked about a little bit this morning, which tries to predict the stock market. And so what you do is you try to learn a thing, and the thing itself is the simplest possible, what's the right word, synthetic kind of example, which is, I'll show you quickly and then slowly. You just draw something in here, and then you see if the network can learn it. And so what you do is you follow the instructions, number one. Number two is create a training file. I'll show you that file a little bit later. And then create a nice network, and then train the network on the file. And then it does this for you. Actually, you might not see that because I've got standard error and you don't. And then you can test it, and what the testing does is run numbers from 0 to 99 through this thing. Oh yeah, the x-axis here is 0 to 99, and the y-axis is -1 to 1, as usual. And then I'll run the network for all the inputs that I just trained it on, and then I'll get this, right? Which is my neural net learned version of this function, right? And then what I'll do is, oh gosh, that was horrible, let's give it more hidden layers, right? So I'll create a new network with more layers, and then I'll train it again on the same file. Train on file. Yar, 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 yar. Oh, you know what? Maybe I need to give it more iterations. Let's multiply that by, I don't know, some large number. Let's try it again. Actually, I can hit this repeatedly, I think. Can I? Train on file, yes. Because it will go off from where it was. And this is this error function, and you can see the same thing as before, that this thing is sort of doing as well as it's ever going to be able to do, because you can see that the error is not dropping any further now.
So, yeah, just to give an information, I was able to, on my Mac, to open the patch just by ticking use Rosetta
Oh,
on the PD
really?
application. Yes.
Okay. So somehow PD inherited Rosetta from the GUI program that started it. I don't know how that happened. I'm glad it happened, but I don't, right? And maybe it will never happen again. Okay. And so it's having trouble training it. This is the same sort of thing that we were seeing in David's example. But if I, and I can't get any better than that. So now let's see how well it did by testing it again. And gee, so it thinks that this thing looks about like that, right? Now, yeah, question?
Forgive me if you already covered this. In my console, I'm seeing not initialized.
That is because, I think, because you have to hit one of these create things.
Sorry, because security and private, I have something that like security, it cannot be open because you're not a verified developer.
Yeah. Oh, that's true. You should never run anything that I wrote because it's always dangerous, right? Music might come out of your computer. It's really a bad security problem. And now, so there's a way that you...
Security and privacy we make a law anyway.
So there is a command line thing that you can do to unprotect a specific program. This is for PureData, or this must be for the plugin, yeah.
But if you go on the Mac, you go to System, Preferences, and Security and Privacy.
Yeah.
It asks you to allow anyway.
Okay. So it lets you in finally. Okay. There's also a command line way you can do it because sometimes you can't get it to do that. I've never understood all that. Just give it some more. Huh. Okay. Right. Okay. So I don't know if are people still trying to catch up? I think you are, some of you. All right. So I think there's something very interesting to learn here, which is that, let's go back to okay, so first off, let me explain a couple of things about this object. So the thing that you downloaded contained both some test patches and also contains this object called Artificial Neural Network Multi-Level Perceptron, which is the thing that we're using here. It's the active ingredient to this example and to all the other examples in this zip file, right? And so what this thing does is, well, okay, so it does this kind of thing. It takes whatever each layer of this thing makes a linear combination of the inputs and then runs the result through this saturation function, and then that's the output, and that's what one of these objects is. And what the neural net does is makes a topology of these things. And in this particular case, what it builds is a topology where you specify the number of layers, and if there are hidden layers in it, which are layers in the middle between the beginning and the ending part of the thing, you specify how many neurons there will be in that particular layer. So here, where I asked it to make 3 layers with the middle hidden layer having 10 objects, what that did was that made, let's see, I think there's 1 input because there's just 1 input number. There's only 1 output that we're creating. And there is a hidden layer with 10 of these things. right? Like that, okay? And so what that's going to do is, well, I don't really even know why the first thing is there because it's just looking at the input. These things then are going to create a bunch of functions, each of which will look something like this. Hello. Okay, so the input is going to range from, wow. Input's going to range from 0 to 99. Right? And each of these functions here is a linear combination of all of the input followed by a sigmoid function. And so what that can do is that can make you a sigmoid function with a specific onset and a specific sharpness. The onset and this sharpness will be then controlled by the two parameters that are here. There's one that I didn't mention, which is you feed it the input network, and you also feed it a non-neuron, which has the output of always 1. So that if these numbers here are A and B, what you're doing is you're computing AX plus B, and then you're saturating it. And that just means make a sigmoid function and move it to left to right or forward or backward, right? And then what we're going to do is take those things and make some linear combination of them, which then can create things that have steps up and down in various places. This is what a linear combination of these things might look like. And then we're going to clip that, which we'll just shave off the top perhaps. And that's what we're going to see on the output here, right? So what that makes us believe, and here's where you're going to see that I don't know what I'm doing. I'm going to make a function that it likes to find out about, and then I'm going to make a function it hates, right? So even with only 3 intermediate layers, if I give it an easy function, like that, that's the kind of function that you can make out of that network that I just showed you in the other page, right? And so if I now train this simple network on, I wrote this in the wrong place. I'm sorry. This is the test. This is nonsense. Go away. This is the thing I want to do. Sorry. Okay, easy test. Well, that wasn't as good as I wanted. All right, good enough. And now generate test file. I've already created it, but we can create it again if you want. And now I'll train it, and it learns really fast. It did pretty well. The error, this is, by the way, a mean square error, so a true error is the square root of this, which is about 1/50th on a scale of -1 to 1. And now if I test it, test, I get, my function back, right? And now I'll do something that it really doesn't want to do, let's see, which is, well, all right. It's got 3 sigmoids, so it might even be able to do this. It might not. We'll see. I'm trying to make that smoother to be nice to it, right? And now, again, make a trainer file. I'll start again with a new network. Train it. Ooh, it hates it. Now this is what failure looks like. Failure looks like an RMS error of 100, which means a mean error of 1/10, and that when I test it, gives me, it just slapped one of them down and gave up, right? Now this, and again, David knows more about this than I do, so ask him, but there are different optimization algorithms that might be better at finding non-local solutions. So problem here is there are, we're already, this is about a 10 or 15 dimensional space we're searching in, right? Because there are 3 neurons, each one has 2 inputs and 1 gain, maybe, I can't remember, and maybe just 2, I can't remember. I think there are 3 parameters per neuron here, and I think there are 4-ish neurons, so maybe we're talking 12 to 15 parameters total. So we're in a big space, and there probably is something that that's much closer to this than it could find, but it couldn't find it because it doesn't have a really smart algorithm. It's probably doing gradient descent. And gradient descent is great if you have something that points you decently well to the global minimum from wherever you are, and does horribly if you have something that's more jagged and messed up, like what I'm giving it to do here. Now, and again, I'm using a very simple, straightforward default learning method. That's to say, optimization method. And if you had a smarter optimization method, you might be able to do somewhat better, but how much better could you do if you had a problem that was 1,000-dimensional instead of just one-dimensional? Don't know. Oh, by one-dimensional, I mean there's one input and one output here, right? Or I could say it's only a 12-dimensional problem because there are only 12-ish parameters in this whole neural net. And it's already failing badly enough that I'm wondering if I'm ever going to spend my time messing with learning algorithms. Except that, actually, you can do cool things with them, as we all see all the time. So this is actually worth pursuing, even though, as I'm showing you, the basic thing that it does is, yeah, I don't know if it even works, right? So let's see this thing that it did a horrible job of optimizing. Let's see if we do better if we give it more neurons to optimize it with. And I'll do this in two ways. One is to just give it more neurons in the middle. I predict it's not going to do any better because it already only really used one to do that. It couldn't figure out that it wanted to use more than one. So let's create a heftier one and train it. Oh, it did much better. And now whoa, pretty good. All right, I was trying to make it hate itself, and I actually did something it liked. Okay. So and last time I tried this, it was just a complete mess. So let's just give it something it really will hate. Okay, create, train. Ooh, it loves that too. Oh wait, I drew wrong one. Sorry, got to mess with the training file. It's cheating to mess with the output file. You're not supposed to do that. Train. Hello. Oh, make file. Yeah, thank you. Make trainer file. Then I don't think I have to create it again, but I'll do it anyway. And now it's it's going in circles now. And now it's going to be bad again. Yeah. Oh, not as bad as I expected. Right? Now, if you were trying to use this to drive you safely to the supermarket, you'd be dead, right? But on the other hand, using this to control synthesis parameters, nobody dies even if it fails, and probably this is not going to sound as bad as you might think it would. Notice also that, all right, so certain kinds of functions are good for these artificial neural networks, and certain kinds of functions are very bad. But the things that it does well and badly are different from the things that, for instance, polynomial approximation would do well and badly. In particular, there's no problem at all with discontinuities. So here's discontinuity city, right? And it just knows that to make a nice discontinuity, what it has to do is just make those sigmoids real super sharp. So this, I predict, no. All right, the reality is contradicting me. Yeah. Sorry, that wasn't true what I just told you was going to happen. It should be the case that it can do step functions just great, and polynomials obviously are not going to be able to do that ever at all, right? By the way, it's not failing because it's not differentiable. This differentiability thing is in the optimization. It is not in the actual function that it's trying to match. That function can be as discontinuous as you want, right? What it, in higher dimensions, what it seems to like to do, so let's go back here and talk about what a sigmoid looks like. Okay, so here is now a graph of a sigmoid. I'm going to just draw. This is like two dimensions of input, x1 and x2. Except, always put me in a. Don't know why it's doing this to me. Okay. Okay. So imagine a plane. I'm trying to draw it in perspective, and now I'm going to draw what a sigmoid looks like as a three-dimensional plot. It looks something like this. Starts down, goes through 0, right where the line hits it, which I didn't get right, like that, right? So there's like a pseudo three-dimensional representation of this nice sigmoid function as it looks like in a higher dimensionality. And now if you have 3 or 4 of those and are making some nonlinear combination of that, you ought to be able to make things that have roughly planar transitions up in this higher dimensional space, but it can have transitions where one plane hits another plane and bends over and then follows that plane for a while, right? That kind of thing. Now, do you think that the thing that you're trying to train looks like this kind of a function? Can you even visualize what that means up in 500 dimensions? No. But can you come up with some sort of way of thinking pseudo-logically about what kinds of functions you might want to try to approximate with this collection of functions? And if not, why are you using multi-level perceptrons at all? It's just a class of functions. There are many, many classes of functions in the world. This particular one was come up with in the 60s by people who oversimplified what they thought neurons were doing in a way that completely abused both the idea of a neuron and the idea of intelligence. And why on earth are we using this instead of some other class of functions? For instance, spline functions. Well, in fact, these are a kind of a spline function, right? But you could actually like make yourself an optimization thing that fits something with splines. In fact, Jean-Claude Risset optimized a trumpet sound by making line segments and just making line segment functions that mapped the amplitudes of harmonics of a trumpet over time, and did this in the 60s. And you can do this in PD. You don't even need any externs. You can just write a patch for it, and it does decently well in one dimension, right? But then, why in 500 dimensions can't you come up with something that is actually designed for the particular problem space that you're in, as opposed to using multi-level perceptrons? The answer seems to be that people have spent a lot of time optimizing these multi-level perceptrons, and they haven't spent a lot of time optimizing whatever the better class of functions is that you might actually be able to think of as a researcher who has a brain. And so maybe you could throw away all of that work on optimizing and actually really think functionally about what class of functions you want to best approximate the shape that you are trying to learn in your computer, right? And that, by the way, seems to me a completely wide open research area that I don't think anyone is really writing seriously about, because everyone's using MLPs. And I don't know why this is true at all, except just from pure inertia. But 40 years worth of inertia. What's going on here? I don't know. And I would like an answer to that someday. Or I'd like someone to break out of it. And let's see, I'm supposed to talk until 10 minutes from now, so questions. And then we'll get back to something that actually does something useful, because what I'm doing is trying to show you what you're all doing wrong, right? And you really want to know what you can do that's interesting and positive, right?
Do you know of any more biologically plausible neurons made or modeled with PD? Because as you mentioned this morning, the activation is kind of clock, more or less.
Yeah.
Fast, and time is super relevant to the way the neuron works. For example, when you have the coincidence of activation and the firing of the neuron, and the learning process takes place, etc.
Right. For instance, your hearing mechanism, the neurons are actually up to a certain frequency are pulsing in synchronization with the waveform that's coming into your ear. So it isn't which neuron is firing, it's actually the speed at which the thing is firing that matters, right? And I don't know of anyone who's doing this, and in fact, I wouldn't look specifically in PD or in computer music to find this. I would look and see if some of the neurologists are trying to make models of actual brains. And I think I'm seeing people work on very simple kinds of neural structures, like zebra finches and things like that, and getting somewhere with figuring out when a zebra finch ought to chirp, and doing it by making a real model of a proper working neuron. But I think that's just wide open, because it's a much, much harder, it's a much, much harder but more interesting problem, I think, than that of multi-level perceptrons. Yeah, that's an interesting thing to find out about. But I'm pretty sure that the people who are doing that well are not the people in computer music. Yeah. Other questions? Or? Yeah. I mean, these are all These are all things that people should write a PhD dissertation on, right? Yeah?
But do you think that Raylu was biologically inspired too, because it has a high clipping feature? You know, it doesn't have any energy at all going into its activation function, and it just is pretty zero now.
Yeah. Well, that's true of my stomp box too, right? Because it can't, it goes from 0 to 9 volts. So that's a thing, but that's much, much more widespread than in neurons. But somehow that doesn't correspond exactly to the question you asked, though. But yeah, clipping is universal. And clipping is powerful, by the way. If you, here's another thing. Let's take the first half of this thing and extrapolate it to see if it can recover the second half. Right? Wouldn't that be cool? But that's the stock market extrapolation problem. Well, I actually made this morning. Here's generate a training file on the left half of this training data only, right? I should show you. I'm going to show you the training file here if I can find it. Yeah. So a training curve for this particular package looks like, here's the number of training points, here's the number of inputs, here's the number of outputs, input 0, output minus 0.4, and so on. And that is this curve, except that in this particular instance of it, I generated a file that only goes up halfway. And now we will train our neural net on that. I guess, I should probably reinitialize, just so that it doesn't have any memory of what it did before. And it's training, and it's training, and it's training, and it's about got as well as it's going to get, and it did. Ha! It predicts that the price of wheat is going to go up and is going to clip at +1. Right? So, good thing about this is that when you're using good thing about this is that when you're using sigmoids to extrapolate. Another point from this morning, everything that you're ever doing is always extrapolating as soon as you get past about 2 dimensions, because you're always outside of the convex hull of the training set, right? But sigmoids are good for this because sigmoids flatten out as they go off to infinity, whereas polynomials, of course, just blow up, right? So even though this has no way of predicting the future, it at least doesn't give you 10 to the 10th for an input value of 100 as it could have otherwise, right, if I was using polynomials. So this is another thing. This is perhaps a reason why multi-level perceptrons weren't such a terrible choice of spline functions to use in these kinds of applications, is that their asymptotic behavior is not exactly well behaved, because it's stupid, it just levels off, but at least doesn't blow up. So it's better to level off than to blow up, I guess. Right? So that's the thing. But there are many other classes of functions that would have that property too that you could think about. All right, it is pushing 4 o'clock. This clock is an hour slow. So I'm going to cede the floor for our next workshop. But maybe there's time for one last question.
I think we have time for questions.
No? Okay. We'll just make a little time for questions. Or diatribes are fine too. Like if someone here is just completely disagreeing with what I'm putting down, then that would be a good thing to find out about. Because then we can have a controversy, and then we can go home and think about stuff. No.
So here you use an external library for that. Would that be possible to develop that purely in PD?
Oh God, maybe, but I think the optimization code is written in C, and I think in PD it would be very slow.
Okay.
So yeah, I wouldn't do it. And in fact, if I were doing this, if I were a lot more serious about what I was doing here, I would reach for, you can embed other programming languages in PD, so I'd be calling one of the vector, TensorFlow, blah, blah, blahs, and doing all my stuff 10 times faster. But as you can see, I have yet to get conceptually past the stage where compute time is even a problem, because I've already got so many conceptual problems just just tracing a one-dimensional function that I can't get any further than that. Yeah. Other questions? Or reactions? Yeah.
Cool.
Okay.